let's analyze the response for this circuit. So what we see here, there is an operational amplifier with a gain A, and the inverting terminal of it is connected to the ground through this resistor R1, and there is a feedback resistor RF connected between output and the input. So the node voltage at the inverting terminal is indicated by V1, and node voltage at the positive terminal is indicated by V2. And the input signal is applied to the positive terminal through this RC network. And what we are interested is to obtain the output voltage. So how to analyze this circuit is basically we first calculate the voltage at node V2 with the help of voltage division rule. So we know that the impedance of a capacitor is j omega c, which will be multiplied with the input voltage Vi, and in the denominator we have a summation of two impedances, which is the impedance of capacitor and the impedance of resistor. So we've tried to solve it further. It gives us the value of and j omega c. From both these terms get cancelled. Finally, we have this value of Vi over j omega Rc, 1 plus j omega Rc. So output voltage, then we know that it's the non-inverting amplifier or the operational amplifier. Non-inverting configuration. So output voltage is given by 1 plus R2 over R1, but we have RF here, so we say that let's call it R1 and let's call it R2. Okay, so it is the 1 plus R2 over R1 multiplied by node voltage V2, which is coming at the positive terminal, and we can solve it. So it gives us the value of V2 has this value. So we plug in here. So what we see here, we can then obtain the ratio of the two voltages, which is output voltage divided by the input voltage. And that comes out to be 1 plus R2 over R1 divided by 1 plus j omega Rc. So that's our output voltage. Now the task here is to obtain the magnitude and the phase response. And the phase. So first of all, we'll try to obtain the magnitude, which is the mod of VO over VI, which would be computed as, we know that here the imaginary part is 0. So it's the square of square root in bracket square of real part plus square of the imaginary parts, which is 0. And what we have in the denominator, again, we have a real part to be equal to 1. So square of 1 plus square of imaginary part square, which is omega Rc square. And we try to solve this. So it comes out to be divided by square root 1 plus omega Rc whole square. Similarly, we can get the value of phase of this output voltages, the ratio of output to the input, which would be the phase of the numerator, which is 0 right here. Why it is 0? Because we can see from this. So this is the real part, real axis, this is imaginary axis, and we see here, somewhere here, we have this 1 plus R2 over R1, that is the 0. because we are trying to obtain the zero and the poles of the transfer function. So zero is here, and the angle, the phase here is zero. Okay, and then that's why we can write here, it's the phase of this numerator is zero minus inverse tangent of the imaginary part, which is omega RC divided by the real part. Okay, so that's the expression for the phase, which turns out to be minus tan inverse omega RC. And where is that pole? Pole comes out to be here. So somewhere here we have a 1, for instance, and somewhere here we have omega RC. That is a 1, right? So we see that somewhere here we have the pole. And the angle would be given by this one. So we'll see how much is the angle there. So let us analyze the three cases. At omega is equal to 0, we try to obtain the magnitude, value of a magnitude, which we plug in the value. So we know that this is the expression for this magnitude. So we know that omega is equal to 0 here. So we try to put in that value. So 1 plus R2 divided by R1, square root of 1 plus 0. So that comes out to be 1 plus R2 over R1. So that's the DC value, what we have it. And the angle for this would be VI, which is minus tan inverse omega RC. So that comes out to be minus tan inverse of 0, which is 0. So here in this plot, we can try to obtain the value of magnitude, that is here. And somewhere here, we see that we have omega is equal to 0 right here. Somewhere here we have omega equal to omega c, and here omega is equal to infinity, or very, very large value. So at omega is equal to 0, magnitude takes the value of 1 plus R2 divided by R1. That is the value of magnitude or gain. Similarly, and the phase also can be drawn here. So we see that the value here is 0. Phi is equal to 0. So in the second case, at omega is equal to omega c, what we see here, that's the magnitude, will be written as 1 plus R2 over R1 divided by square root of 1 plus omega is now omega c. Okay, and here we have RC. So it's nothing but 1 plus R2 over R1 square root of 1 plus 1 by RC. Now omega c is 1 by RC actually into RC. So that comes out to be 1 over root 2, 1 plus R2 by R1. So we see that the gain drops by the factor 0.707. So it's 1 by root 2 is 0.707. So we can draw that. So up to this point, right here, we see that the gain is constant, but then thereafter, at this point, it drops to a new value, and this value is 0.707 times 1 plus R2 over R1. Fine. What about the angle? Angle would be calculated as VO by VI, that is minus tan inverse of omega RC, which is minus tan inverse of omega C into RC inverse 1 by RC into RC. So it comes out to be, this cancels out. So it's minus 45 degree. So at this frequency, we see that the phase approaches minus 45, right, somewhere here. All right, final case when the omega is very, very large. So let's say omega is very, very large than omega c, or we just say that omega is equal to infinity. In that case, what we see that the magnitude will take this value, which is 1 plus r2 over r1 square root of 1 plus infinity. So that comes out to be 0, obviously. And the angle would take the form of minus tan inverse of infinity. So that comes out to be minus 90 degree. So we see that when omega is very large, the value of the gain is approaching 0 and the phase is approaching minus 90. Let's say it's called minus 90 degree. So that's how this circuit behaves. It's a response of the low pass filter. We see that this is a low pass filter. And the operational amplifier has been used in the non-inverting configuration. Right. So we can compare the two cases where we can use the op-amp in the inverting amplifier. Inverting amplifier in the sense we had this configuration where positive is grounded and we connect the capacitor in the feedback and the resistor R2 and R1 is there as before, which sets the gain, and the capacitor extra is added. And here we have input voltage and there we have output voltage. So if we compare these two configuration, both act as a low pass filter, but the difference is in the phase shifts and the required values of the gains. All right, so that's all for this network. And we continue some other practiced examples as we move ahead.